example, which is problem 10 in the problem set 5.1, which is 1 minus x squared times y double prime minus 2xy prime plus 2y equal to 0. Now, this problem is also example 3, which you can go through and look at the solution. I'm just putting out the final answer here because we can go through the steps using the power series method and we'll end up here. What I wish to focus on is this equation happens to be a special case of a more general equation called Legendre's equation, which is written as 1 minus x squared times y double prime minus 2xy prime plus n times n plus 1 into y equal to 0, where n is a real constant. It need not be an integer all the time, but if it is an integer, it results in a lot of simplifications, one of which is a function that looks like this. So first we are going to look at or discuss the case where n is any real number, and later we'll say what happens if n is a positive integer. Okay, so I want to start with this, derive a general formula for the coefficients of the power series, and then see how the solution looks like. Okay, we are just going to apply the power series method to this equation, starting with y of x equal to summation m runs from 0 to infinity am x power m. This is where we start always, right? And since this function has the is multiplied by 1 minus x squared, the equation, or actually I should write the coefficients of this equation, the coefficients of y double prime, y prime and y, which are respectively minus 2x divided by 1 minus x squared and n times n plus 1 divided by 1 minus x squared. Okay. The coefficients of these two terms, y prime and y, are analytic at x equal to 0. That is, if you put x equal to 0 in the denominator, that denominator isn't 0, which means these coefficients are bounded at x equal to 0, and they do have singularities at x equal to plus minus 1. So we'll seek solutions, but we will ensure that x does not take the value 1, either plus 1 or minus 1. So as far as x equal to 0 is concerned, this is a valid representation of the solution, because if you put x equal to 0, this ODE does not blow up, or the coefficients do not become infinity. Okay. So if we have y prime, or if we have y of x equal to m equal to 0 to infinity am x power m, you can write y prime of x is summation m equal to 1 to infinity m am x power m minus 1. You can do that, right? Obviously, the first term will vanish because when you did the differentiation, a0 will go away. That's what I've written here as m runs from 1 to infinity mam x power m minus 1. Differentiation operation. I can also write y double prime of x equal to m equal to 2 to infinity m times m minus 1 am x power m minus 2. Okay. So I want to obtain terms which are xy prime and x squared y double prime. So I can compute those. This implies xy prime equal to summation 1 to infinity m times am times x power m. I just have to multiply this by x, which is x power m, And I have to multiply this by x squared y double prime, or multiply y double prime by x squared, which is m equals 2 to infinity m times m minus 1 times am times x power m. Are you okay with these operations? You got a question?
Guess I'm confused on why I'm multiplying it by x teacher.
Because we will eventually substitute it back in this equation. We are just preparing the terms which we are going to need in a moment. Okay. So if you substitute this, you substitute for each of these terms, y double prime, x squared y double prime, xy prime, and then y. Okay. I'm going to do that. I have summation m equal to 2 to infinity m times m minus 1 am x power n minus 2. That is the first term. And then I have x squared y double prime. So minus m equals 2 to infinity m times m minus 1 am x power m. And then I have minus 2xy prime minus 2 summation m equals 1 to infinity m am x power m plus n times n plus 1 multiplied by y, which is summation m equal to 0 to infinity am x power m, and this is equal to 0. So this is y double prime x squared y double prime xy prime y. Nothing fancy, right? You are with me so far? Okay. Is anyone still writing these in your notebook? Yeah. Can you hurry up, please?
So it's all you did all that you did is just turning each, I guess, section into a power series.
Correct.
Okay.
That's all I did. And each power series does begin at x power 0. That is, if you put m equals 2, this starts at x power 0. This starts at x squared, though, because of the multiplication by x squared. This starts at x power 1 because of the multiplication with x. And this starts at a naught or x power 0 as intended. Okay, but erase this part. So I'm going to just, you can do it two ways here. You can do a shift of index to make sure all of them have the same index, like same x power m in appear in each summation. Or you could just stop here and start comparing the coefficients of x power m, like x power 0, x power 1, and so on. So I'm just going to shift under each summation, shifting the index appropriately. Okay, so I'm going to write this is s equal to 0 to infinity s plus 2 times s plus 1 as plus 2 x power s. Can you tell me what have I done? this summation and this. Yeah.
So now it starts with 0.
I just took m minus 2 and started calling it s. So wherever m minus 2 m minus 2 appears, m equals 2 will represent s equals 0. Right? I can write m equals s plus 2. Wherever m appears, you have to substitute s plus 2. Start the counting from 2 units later. Okay. Similarly, I'm going to do the same thing here, minus summation s equal to 0 to infinity s plus 2 times s plus 1 times as plus 2 times x power s plus 2. Because here it's only x power m. Wherever m appears, I have to replace it with s plus 2. Okay. But that holds true only for the first and second summation terms. For the third summation term, similar idea, except I'm going to do m minus 1 equal to s or m equals s plus 1. So this is for 1 and 2. This is for 3. We call this 1, call this 2, call this 3. So then I have minus 2 summation s runs from 0 to infinity s plus 1 as plus 1 x power s plus 1. If I call this summation number 4, I don't have to do anything here, but I'll start using s instead of m just to keep it consistent. So I'll have plus n times n plus 1 times summation s runs from 0 to infinity as x power s, and the whole thing is 0. You're with me? Yes? Okay. Is anyone still working on the right side? Right side? Can erase? Yeah. Remember, n is just any real number. Okay, we haven't committed that n is an integer or anything, just any real number. So everything is now in terms of s. Okay, so if you just take any value of s, for example, let's say if you are considering the coefficients of x power s and s is equal to 0. I'm sorry. What I meant to say was, let's say you take the value of s equal to 0, what will you get? I'm sorry, I apologize. I want to get the coefficients of x power s equal to 0. Yeah.
Why didn't we multiply the previous equation with x squared the first place?
What do you mean? Why should we multiply by x squared?
So it will eliminate by, like, the first term was x power n minus 2.
We did multiply by x squared and then x here. Inconsistent with these two terms.
Yes.
I don't understand your question. We'll come back to it maybe later. So if I consider the powers of x power 0, that would be 2 times 1 multiplied by a2. That is, if I put s equal to 0, I'm going to get x power 0. and that will be 2 multiplied by 1 times A2. Okay, and if I put S equal to 0 in this term, this power series will still not have x power 0. Do you see that? It will start only at x squared because S takes values of 0, 1, 2 and so on. So it can only have minimum of x squared. It will never have x power 0. So it doesn't contribute to this. Similar argument, this will start at x power 1. It will not contribute. And then we have this term plus n times n plus 1 multiplied by A0 equal to 0. Or A2 equal to minus n times n plus 1 divided by 2 times 1 times A0. I'll do just one more example. Okay, I'm going to do x power 1. Can you do that and look up? Can you try? Are you also getting this?
Guess I'm kind of confused what you mean by x power s equal to 1. Like, are we saying that?
Okay, let me rewrite this, saying if I set s equal to 0, I want to collect the powers of x power 0. And when I say s equals 1, I want to collect the powers of x power 1.
Okay.
And similarly, next we'll do s equals 2 and collect the powers of x squared. All you have to do is look at this, although it's not written in a very linear fashion. Look at this big equation, and from that collect the powers of x power 0, x power 1, and so on. Yeah.
The and plus 1 should be minus this. On the right.
Yeah. So this is minus.
Yeah.
Let's say this is minus and this is, no, this is, yeah, this can remain minus.
Yeah.
I mean, I write it this way because later we are going to generalize. I don't want to simplify now. Let's do x squared. I want to put s equals 2 here. So that is 4 multiplied by 3 multiplied by A4 minus, again, I can put s equals 0, 2 times 1 times A2. And then the third summation, I need to put s equals 1. So that is minus 2 times 2 multiplied by A2 plus n times n plus 1 times A2 equal to 0. You can sort of see a pattern coming up. Maybe A4 is negative of n times n plus 1 minus 2A2 minus 2 times 2A2 divided by 4 times 3 times A2. It's all deliberate that I'm leaving it like this. Okay. Now you can do this exercise. Let's say you collect the powers of x power s, or yeah, let's say you collect the powers of x power s. Can you try writing that relationship? If you want x power s, you would take the first summation and write s plus 2 times s plus 1, wouldn't you? If you take x power s in the first summation, that will be this term. That's the coefficient of x power s, a s plus 2. If you look at the second summation, you can take a pause from writing. I'll give you time to write. Okay, just take a pause. If you take the second summation and you want the powers of x power s, what do you need to do? Instead of applying the value of s, you need to consider the value of s minus 2, right? So that would be minus s times s minus 1 times as. I'll give you time to write, promise. What about the third summation? Please answer. I need x power s minus 2 s as, because you need to think about the value of s minus 1. So wherever s appears, replace it with s minus 1. Okay, and then the last summation, n times n plus 1 times as equal to 0. Now you may write and catch up. See, I promise. There's your formula that connects a future value of the coefficient with a current value. That is, this connects A0 with A2, A1 with A3, and so on. These type of formulas, as you may already know, are called recurrence relations. I can rewrite this solution whenever I want. I need the space. Can I erase the? No, I don't want to erase the left side. Kind of being into our discussion. Okay. With me so far? Okay. So can you rearrange and get as plus 2 is equal to as multiplied by something? What is that something? That something would be, I can even write minus as times n plus 1 minus s times s minus 1 minus 2s, right? 2s divided by s plus 2 times s plus 1 right? Okay. So what will this be? You can do some simplifications maybe. Squared minus. So the book does some simplification, but let's see if we can actually catch that. N squared plus n minus s squared plus s minus 2s. So this is minus s So this is n times n plus 1 minus s times s plus 1. Oh, I see what they're doing. So they are writing n minus s times n plus s plus n minus s, which is n minus s times n plus s plus 1. So my as plus 2 is minus as times n minus s times n plus s plus 1 divided by s plus 2, s plus 1. Are you? So this is our recurrence formula, which sort of describes future values or later values of the coefficients. And we still haven't told what n is. N can be any real number. That's the assumption so far. Okay. All right. So as you can see, if you substitute s equal to 0, you are going to get a2 in terms of a naught multiplied by n times n plus 1 divided by 2 times 1. Or I'll write this as minus n times n plus 1 divided by 2 factorial times a naught. And s equals 1 is going to get you a3 equals minus a1 times n minus 1 n plus 2 divided by 3 times 2, which I can write minus a1 n minus 1 times n minus 2, sorry, n plus 2 divided by 3 factorial. What am I going to say next? You've been in the class for 4 lectures now. A2 in terms of A naught, A3 in terms of A1, and a recurrence relation that is S2, S plus 2 in terms of S. What's next? You know the answer and you just don't want to talk? Or you don't know the answer? Come on, say something. That is A naught and A1 are the only constants which are truly unknown. Everything else is known in terms of those two. So if we have to collect them as functions, you can collect or you can write y of x equal to a naught multiplied by say function 1 and a1 multiplied by function 2. I'm sorry, a naught y naught plus a1 y1, because those two are the truly unknown constants. Everything else is known. And if you had boundary conditions, you can evaluate what are a naught and a1. Until here we are okay, right? Okay. So now, actually, if I write it this way, and for consistency's sake, I'm going to use y1 plus y2 because that's what the book uses. So I'm writing y of x equal to a naught y1 plus a1 y2, where y1 of x equal to, you need to collect all the terms which are going to depend on a naught. Can you tell me which are going to be those terms? All the even powers. All the even powers are going to be depending on a naught. So I'm going to write a naught times 1 obviously first term is a naught. And then I will have, remember, a naught plus a2x squared plus a4x to the 4 plus and so on up to infinity. And then the other series is a1x plus a3x cubed plus a5x power 5 plus and so on up to infinity. So I can write the first summation, sorry, this is just the second function. So I can write y1 of x equal to a naught times 1 minus n times n plus 1 divided by 2 factorial, n times n plus 1 divided by 2 factorial x squared. And if you did calculate A4, A5 manually, you're going to get this. So I'm just going to copy this result from the book. Plus n minus 2 times n plus 1 times n plus 3 divided by 4 factorial x to the 4th. And the next term in the series is going to be a negative term. So we'll just say dot, dot, dot. That is your y1. See, this is your y1. The way I have written it, a naught times y1. And it's the nomenclature. So we'll make a correction here. Say it's y1 plus y2, where y1 includes the constant, and similarly y2 is going to include the constant. a1 times x minus n times, n minus 1 times n minus 2 divided by 3 factorial x cubed plus n minus 3, n minus 1, n plus 1, n plus 3 divided by 5 factorial x to the 5th minus dot, dot, dot up to infinity. For the example I started at the end of last lecture, which if you recall, 1 minus x squared times y double prime. You can get this equation by setting n equals 1. That's obvious to you, right? This equation, which we saw as started as an example, is just a special case with n equals 1. You can substitute n equals 1 in this formula and see what solution you're getting. In that case, y1 of x is going to be a naught times 1 minus n equals 1. 1 times 2 divided by 2 factorial. So that's x squared, right? Yeah, x squared plus I have n equals 1 minus 1, 1, 2, 4. 2 times 4 is 8 minus 1 minus 8. 8 divided by 4 times 3 times 2 times 1. 1 by 3. Wait, yeah, sure. 1 by. So that's minus 1 by 3 x to the 4th minus and so on up to infinity. That is one of the basis functions. By the way, what is the basis function? If I write my solution as the sum of two linearly independent functions multiplied by a constant, those linearly independent functions are called basis functions. Okay. Y2 of x would be what? Luckily for you, n equals 1 eliminates all the higher order terms from 3 onwards. So you're left with y2 of x equal to a1 times x. That's a linearly independent function, right? If you look at this is a 1 minus x squared minus x to the fourth, and then you have the function x. Can you say these two are linearly independent? This polynomial, this infinite series and the function x, are they linearly independent? If you divide them, you can't reduce them to a constant, so they are linearly independent. So here is the general solution for any value of n, okay, any value of n, and here is a particular case where one of the basis functions is an infinite series and the other is a polynomial of order 1. It just happens that this n equals 1 and this happens to be a first order polynomial. As we'll shortly see, this is called the Legendre's polynomial of order 1. Order 1, which we denote P1 of x. We are going to see Pn of x in general shortly. If you are okay with going through this tedious process every time you encounter this equation, that is, every time you find, wherever you encounter this equation, this is the Legendre's equation with which we started. If you are okay with going through all these steps to arrive here, every time you meet this equation, then you can stop here. But it turns out whenever n is a real number and also an integer, this equation need not be solved from scratch every time, and you could use Legendre's polynomial to construct solutions. And that's why we are learning what are those polynomials. Okay, so we want to take this recurrence formula. Okay, up till here, n is any integer, or sorry, I beg your pardon, n is any real number. But if we then place the constraint that n is an integer, some interesting relations or simplifications come thereafter. Okay, so until this step is always true. I want that to be clear. Okay, so now we'll look at the special case. Any questions? Like, am I going too fast, too slow? Something not clear? Are we okay? Everyone's looking away. That's usually a bad sign. So this is for any integer, okay? All right. So if you take this equation, the next step is to write as plus 2 is minus as n plus s plus 1 times n minus s divided by s plus 2 times s plus 1. This is where we started, right? As you can easily observe, whenever First of all, what is the constraint we are placing here? N is a positive integer. N is a positive integer. That's the constraint. 0, 1, 2, and so on. I might as well write that n equals 0, 1, 2, and so on. So whenever s equals n, a s plus 2 becomes 0, or a n plus 2 becomes 0. That's obvious from this relation. Okay. And an integer can either be odd or even. Depending on that, either your even powers become finite or your odd powers become finite. Am I saying something that's too obvious that you don't want to engage with me in that conversation? No? All right. That is what I'm saying is if I choose my n equals 1 like we did here, you saw that all the odd powers after from 3 onwards just vanished. If you had an equation that is 1 minus x squared times y double prime minus 2xy prime plus what is n equals 2? That will be 6y equal to 0. This will be n equals 2. Can you just for a moment compute the solutions or write down the solutions? You write down the solutions. y1 of x would be, I'm going to put n equals 2. So everything from this term goes away. That will be a naught times 1 minus, this is 2 times 3 divided by 2, that's 3x squared. And y1 or y2 of x would be a1 times x. They made some mistake here. In plus 2. We check that. N plus 2. N plus 2. So this will be x minus 2 times 4 divided by 3 factorial. Sorry, 1 times 4 divided by 3 factorial, which is 2 by 3, right? N equals 2. So that will be 1 times 4 divided by 3 times 2. 2 by 3 x cube, and then plus, this is minus 1 plus 1, 3, 5. 15 divided by 5 factorial. So that is 1 divided by 4 times 2, or 1 by 8. Plus 1 by 8 x to the 5 and so on up to infinity. So here you get a polynomial, and here you get an infinite series. Whatever happened in n equals 1 is the opposite of this, right? One became a polynomial, the other became a infinite series. And you can see this will keep on swapping. For n equals 3, it will be the other way, n equals 4 and so on. You can keep doing this. Okay. So now our goal is to derive a formula for am, the coefficient that appears along with, say, let's say am x power m. We want to get a formula for am that is easy to write and can be programmed in maybe when you're writing a code for this or whatever. Yeah.
So that polynomial is called Legendre's polynomial of order 2.
Yes, as we will see, this is the Legendre polynomial of order 2. We'll see a small rider here. That is, this coefficient, as you know, is arbitrary. And in your problem solving process, how do you actually get these coefficients or the value of those coefficients? Through your boundary condition. What we are going to see is slightly different from that in the sense, by choosing specific values for the coefficients A0 and A1, instead of writing the solution as y of x equal to A0 times something plus A1 times something, we want to write it as, let's say, C1 times Legendre polynomial 1, not 1, I should say Pn of x plus C2 times an infinite series. So that we are going to choose a specific value for A0, which you can later adjust, because when you apply the boundary condition, it is going to dictate what C1 is. So think of C1 is A0 multiplied by a choice. I'm going to call that choice alpha to make this equal to Pn. It's just a small adjustment that the mathematicians chose to make this simpler, so that instead of going through the process, all you can do is just look up the table and write down Pn of x. Okay. So to do that, we are starting with, you are having this as plus 2 in terms of as, right? We are going to flip that and write as equal to minus s plus 2 times s plus 1 divided by n minus s divided by n plus s plus 1 as plus 2, where s ranges is no more than n minus 2. And we do have n comes from the ODE. So n is not something you get to choose, n is just given to you. So don't be thinking what happens if n is 5 or 0 or 1. You don't have a choice in that. It is what it is. And whatever that integer is, s is bounded as n minus 2. Okay. N comes from the ODE. And I told you about a convenient choice for this alpha, right? What they want to choose is an to be 2n factorial divided by 2 power n factorial squared. Why this choice? Frankly, beats me. Okay, I want to tell you what I don't know, so that I'm being transparent with you. Okay, so if you go through a series of steps, what you're going to get is this. This is the golden formula. A n minus 2m equal to you're yawning. Can you just cut out the sound? The sight I can escape by looking this. Okay, what is m here? M is just a regular integer which runs from 0, 1, 2, 3, like a counter. And we are going to use this formula to generate even and odd values of the function. I'm sorry, the coefficients. So if you write Pn of x, Legendre polynomial of order n is written as summation. Maybe I shouldn't write it here. I'll find a more central location. Pn of x is summation m equal to 0 to uppercase M minus 1 power m 2n minus 2m factorial divided by 2 power n m factorial where uppercase M equal to n over 2 if it is a if n is even, if n is even, and m equals n minus 1 over 2 if n is odd. So if you want to construct the zeroth order polynomial, which is n equals 0, so you have to choose m equals 0. That would be minus 1 power 0, 2n factorial, sorry, 2n minus 2m is 0. So this is just 1 factorial 1 divided by 2 power 0, 0 factorial, 0 factorial, 0 factorial, multiplied by x power 0. Nothing but 1. The zeroth order polynomial is just 1. The first order polynomial, P1 of x. You would run the summation from m equals 0 to what value? If you were to choose the upper limit, when n is odd, uppercase M is n minus 1 over 2. So this will be again 0. So there is only one value of m to run, which is m equal to 0. But there is a small twist. N is 1, right? So this is minus 1 power 0 divided by 2 factorial. I'm sorry, multiplied by 2 factorial, 2 power 1, 0 factorial, 1 factorial, 1 factorial, multiplied by x, multiplied by x power 1, which is again 2, 2. So this is just x. So the zeroth order polynomial is 1. The first order polynomial is x. X is n is 1. The only value of m which you are allowed to consider is 0. So this is a 1 minus 0. That's why it's just 1.
I guess I just saw -1 raised to 0 in the.
Negative 1 raised to the 0, we are considering this equal to 1. If you look at figure 107, you can find a neat graph of the Legendre polynomials for up to n equals, I guess, 4. That is, for each value of n, you get a polynomial of increasing order. N equals 0, 0th order polynomial. N equals 1, linear. Second order, third order, fourth order, and so on. Okay. So what do you need to learn here? What do you need to be able to do after this exercise? Here's what you need to do. If you see this equation, 1 minus x squared times y double prime minus 2xy prime plus n times n plus 1 times y equal to 0. What is always the goal? The goal is to be able to write solutions to this equation. You can write this is y of x equal to C1 Pn of x. Okay. And the other will be an infinite series. Right? There will be a C2 multiplied by an infinite series. So if in the same formula, you're going to apply either odd or even values of n, you're going to get different number of terms, but all of this is just a polynomial. You're not going to get the other series or other solution. Sometimes your boundary conditions may, keyword is may, lead you to a situation where the other infinite series solution doesn't matter, where C2 is 0 and C1 happens to be non-zero. Why am I so sure that it may happen? First of all, I'm not sure, I'm saying may, but I am saying it is likely to happen because this equation is a model equation that describes diffusion equations and many second order differential equations that occur in spherical polar coordinates. You will see this when we do partial differential equation. You start with a spherical polar equation. It reduces or it decomposes into 3 different equations, one of which is this equation. And usually instead of x being the dependent variable, we'll write it in terms of radius. Okay. In such spherical domains, remember your r always varies between 0 to some finite value. And most of your functions cannot become infinity or they do remain bounded. It will just so happen that you will have a boundary condition called dphi over dr is 0 at r equal to 0. This is called the symmetry boundary condition. This boundary condition will invariably help us get rid of the other part. So you could almost use one of them to eliminate the infinite series and be left with a Legendre polynomial. It could be like a sphere whose surface temperature is given to be 100 degrees and you're asked to calculate the temperature profile inside the sphere. Or it could be a sphere whose surface temperature is 100 degrees and you're asked to calculate the surface the temperature of the space outside the sphere from r equals radius to r equals infinity. In either case, you will end up with this kind of an equation. Not only there, in most problems where spherical symmetry is found. Okay. So usually we say the solution is a constant times Legendre polynomial, and that constant comes from boundary conditions. Okay. So the skill that you need to pick up is to be able to look at such an equation, identify what n is, either n is a integer or it is not. If it is not an integer, we wrote down an infinite series at the beginning, we go there. If it's an integer, you write it in terms of Legendre polynomials. That makes sense? The sequencing, okay? All right.
When you talk about it's not an integer use thing we used earlier, was that the AS plus 2 is equal to negative AS, and then if the
Yeah.
n plus 1.
That will be the general case. The general case will work all the time. It's just laborious, it's a lot of steps. But this is a useful simplification whenever you have one of them to be an integer. Sorry. Whenever you have n to be an integer. Okay? All right. So let's try an example. I want you to try problem set 5.2, problem 2. I mean, when I say I want you, let's try. I also want to try with you. Problem set 5.2, problem 2. Take a minute, please read the problem. And as you go through this problems and this chapter, start thinking about your project 1. For project 1, you need to pick an engineering problem or a physics problem, and that is described by an ordinary differential equation, and use the methods developed in this special functions module 2, to solve it. It could be like a heat diffusion problem, could be a beam problem, could be bending, whatever. But some kind of engineering problem which has to be solved using the methods of ODE solutions, power series. So let me take a poll of what kind of engineers do we have in this room, like mechanical engineers. Okay, most of you are. Oh, in fact, all of you. No civil engineers here, no biomedical, no electrical engineers this time. So maybe can I ask you, like, what are your favorite topics? Like, you can go around, feel free to say what you like so that I can later help you to pick one problem out of there. Go ahead, just say what you like. Heat transfer. I heard fluid mechanics. Okay, what else? What are the fatigue? So you'll have to come with your own problem. I have zero knowledge about fatigue. Okay. Sorry? Thermodynamics. Okay. We are going to, it will be very hard to find ODEs in thermodynamics. They all do steady state stuff that we'll find. Dynamics. Okay. Dynamics. Heat transfer. Okay. So can anyone, like among you, say one problem or one situation which you can model using an ODE? Like describe some engineering problem if you can think of. I want to see who has thought about it a little bit. Okay. So let me give you one simple example. If I think of this base which is at, let's say, T1, and I'm thinking of a fin which can also develop as like a cantilever problem, but I know heat transfer a little more better than I know structures. So if I write an equation for the temperature profile in this fin, and if this is my z-axis, invariably I would write minus, I'll say del dot minus K del T plus any heat generation should equal to 0. I write it this way, but I can also write it minus K d squared T over dz squared plus Q equal to 0, where I can say Q is a volumetric heat generation term which can vary in a funky way. It could be that there is additional computer chips that are distributed here and here. So Q of Z is non-zero at this point and at this point, but everywhere else it is 0. So I have like a point source at 2 points, and everywhere else the heat generation is 0. But my goal is to say, or to figure out, what is the temperature profile for this function or for this fin. So this is just an example of how I would think about it if I were you, to pick one engineering problem But to make it meaningful or something that is representative of what you do in your other coursework or your research, so that you can apply and derive an equation or an ODE. And then how would you solve this? You very well know that if Q is a complicated function, you can use power series method and then figure out a solution for T, depending on the boundary conditions. So boundary conditions here is H times T minus T infinity equals, like, I'm talking about the heat transfer coefficient. So, sorry? I'm talking about a natural convection boundary condition here, which apparently I've forgotten at the moment. Anyway, you will know better. So this sort of like, I want you to end up with the ODE. What I will ensure is that I look at your problem and make sure it's not too easy. Students always tend to pick things that are very easy to get through the assignment. I want it to be reasonably challenging so that when you solve it, you will learn something and you will be able to articulate it to the rest of the class. Of course, the first assignment is a written submission, so only I will be reading it. But the second submission is going to be a presentation where you will talk about what you did and explain it to the rest of the class. So you need practice for that. Yeah.
It has to be linear, right? Because we haven't discussed any nonlinear methods for second order differential equations.
Yeah, it has to be linear, no nonlinear problems. Because all the ODEs, you can have functions that depend on the spatial variable, but you can't have t squared, no nonlinear. See, if you want to have discussions, please do that outside the class. It's very distracting when some people are talking. Okay. You try coming here and speaking when I sit there and keep talking as I wish. You'll find out. Okay, I want you to try problem set 5.2, problem 2. So for n equals 1, we are asked to prove, of course, one of the functions is P1 of x, the Legendre polynomial of first order, which is easy to write and which just happens to be x. I talked about the other infinite series, right? We are asked to show y2 of x equal to 1 minus half x times natural log of 1 minus x divided by 1 plus x. Remember this, the infinite series can't be wished away. Most of the times it may vanish, but it is there in a mathematical sense, but in a physical sense, the boundary conditions may help you get rid of it. So don't automatically assume that the C2 is 0. Check for it. Okay. How do you prove it? How do you prove this? So when you did the solution, that is when you did the derivation without assuming n is an integer, we wrote y1 of x equal to 1 minus. I'm going to write a few terms, x squared plus n minus 2 n plus 1 n plus 3 divided by 4 factorial x to the 4 minus and so on up to infinity. Now we are thinking about n equals 1. If you put n equals 1, obviously this does not reduce to a polynomial. It is still an infinite series, but you can go ahead and set n equals 1 and see what function do you get. I guess this is y1 of x. This is y2 of x. This is y1 of x, and they are asking us to prove y1 equal to this. So we are going to write out this function and see if it can be simplified into this. So this is a real exam problem where you are going to be asked to simplify this infinite series, group the terms to see if this can be identified as this function. Sounds implausible, sounds like, to me it sounds impossible. How the hell is this going to become this? You'll have to think through it. Okay. What is this function? N equals 1. I have 1 minus x squared, and then this is minus 1, 1, 2, 4. Minus 2 times 4 divided by 4 times 3 times 2 times 1 x to the 4. And remember, where are we getting this? As plus 2 is as minus as n minus s times n plus s plus 1 divided by s plus 2 times s plus 1. So if you want to write higher order terms, you keep referring back to that formula. So I want x power 6. What do I do? If I want x power 6, I need to substitute s equals 2. Okay, take a few minutes, try this, and then let's meet up after 5 minutes. Okay, I'm going to try, you also try, and we'll see how far we can get together. If you're like me, not a very, not that intuitive to just stare at this and say, oh yeah, this is equal to this. What I would do if I'm in the exam trying this question is try to expand this as a power series, which you can always do, and try to show that these two are really the same. And to expand this as a power series, you don't have to go through Taylor series or Maclaurin series. You very well know this. What is ln of 1 plus or ln of a over b? That is just ln a minus ln b. You know this to start with. So you can write ln of 1 minus x minus ln of 1 plus x. You know the series for these. These are elementary functions, right? You know the power series for ln of 1 plus x and 1 minus x. What are these? Okay, before that, let me back up for those who are still trying. Let me go through what I did so that we are all caught up and then we can do the final step. I took this formula. Of course, my n is equal to 1, so I don't have to keep treating it like it is some general variable. I wrote what is the formula in terms of s alone, and a simplification allowed me to write as plus 2 is as times s minus 1 divided by s plus 1. Okay, and s runs from 0 to infinity. That is the idea of the power series. So s equal to 0 gives me a2 in terms of a naught. S equals 1 gives me a3 is 0, and from there on everything else is 0, which makes sense because this is what corresponds to the other solution, which is the Legendre polynomial. It is just a1. A1 is the Legendre polynomial of order 1. Okay, so you can forget about the odd powers and just focus on the even powers 2, 4, 6, and so on. At each step, you're going to get A4 is minus 1/3 A naught, A6 is minus 1/5 A naught. And by just staring at this, I'm able to generalize AS is minus A naught divided by S plus 1 with the constraint that S is even. S minus 1, S minus 1, 6, 5, 8, 7. S is even. Are we together so far? Yeah. So now I have a recurrence relation. A6, 5. So I'm writing the relation between AS and what appears below here. Oh, you're saying, yeah. So 5 is S plus 1. Okay. Thank you. 5 is S plus 1. So I'm still collecting these coefficients, which none of it changes the next step. So we are okay. So you get A naught, 1 minus x squared minus x cubed by 3 and so on. Then you have to understand the question, is this series same as this function? That is what is asked of you, to show that these two are equal. Now you can write, I'm going to erase this, right? AS is minus A naught S plus 1, S is even. Keep it here. All right. What is the power series for logarithm of 1 plus x? Can anyone recall? It's an elementary function. You can see it at the front of your book. Ln of 1 plus x is 1 minus x plus x squared over 2 minus x cubed over 3, I think. Correct me.
No, I guess it's x minus x 2 over 2 plus
X minus x squared over
2 plus x to the power of 3 over 3. I'm saying this based on our previous two sessions.
okay. All right. So ln of 1 minus x is just replace x with minus x. This will be minus x squared over 2 minus x cubed over 3 minus x to the fourth, plus and so on up to infinity. You want their difference. So if you take the difference, the odd powers are going to add up and the even powers are going to cancel. Right? So if you want to get ln of 1 minus x divided by 1 plus x, that would be, I wrote it like, you need to subtract the first row from the second row. Okay, just remember that. This will be minus 2x minus 2x cube over 3 minus 2x to the fifth over 5 and so on up to infinity. I mean, this is obvious from here. So I need minus half times ln of 1 minus x over 1 plus x. So I'm just going to multiply the right side also by minus half, which is going to leave me with x plus x cube over 3 plus x fifth over 5 and so on. And finally, I want to add 1. No. So I want to add 1 to both sides, right? Right? Function. So 1 minus half ln of 1 minus x divided by 1 plus x is 1 plus x cube over 3 plus x to the fifth over 5 and so on up to infinity. What are we missing here? I just want to make sure we got the series for logarithm correctly. Minus 1. So log of 1 minus x series is correct. Okay, this is correct. So log of 1 plus x would be, you need to replace wherever x appears, you need to replace it with minus x. So this is also correct. Okay. All right. Are we on track? Doesn't look like that to me. So this is our function, right? Okay. Okay. Did I write this correctly? Minus a naught. A2. I'll have a naught plus a1 times x. Both these two values are undetermined. Okay. And then I'll have a2, which is minus a naught x squared. Minus a naught x squared plus a1, I'm sorry, a3 x cube. What is a3? 0. That goes away. And then I'll have A4, which is minus 1/3 A naught x to the fourth. X to the fourth minus 1/5 A naught x to the sixth minus 1/7 A naught x to the eighth, and so on. Is this same as this function? That is what we are asking.
So 1 minus 1 over 2x times the,
This one?
yes,
Or what?
you missed x right there.
I missed an x, right? So I have this function, I multiplied this by minus half until here we are okay. I need to now multiply by a x, right? Right? So this will be x squared plus x to the fourth over 3 plus x to the sixth over 5 plus and so on up to infinity. And then if I add 1 to both sides, 1 minus x over 2 ln of 1 minus x divided by 1 plus x to 1 plus x squared plus x to the fourth over 3 plus x to the sixth over 5 and so on up to infinity. What are we getting here? This is A naught plus A1x minus A naught x squared plus x to the fourth over 3 plus x to the sixth over 5 and so on up to infinity. I should clear some space. Okay, how do we reconcile this expression with this expression? Ooh, 7 o'clock. Okay, my wife's going to be mad.
Supposed to be ln of 1 plus x over 1 minus x.
ln of
Just in the original equation, like where you have it show, like right on your left.
here.
Like, yes, because it should be ln of 1 plus x over 1 minus x.
Okay. Let me check if that's what the problem state. Yes, you are right. 1 plus x divided by 1 minus x, which changes a lot of things. Let's pick this up as the first thing for next lecture. Okay. Please try at home. If you can get the solution, good. Thank you.